Continuing with section 2.3, this is the last example. Suppose S is the inverse transformation of T satisfying equations 1 and 2. Show directly that S is linear. So there are two properties that we have to prove if you recall for S to be linear. So we have to show that S of some two vectors u plus v is equal to S of u plus S of v. Okay? And then the second one is that S of R times U is equal to R times S of U. So these are the two statements we have to prove. Okay, for the proof, we start with let U, V be in Rn such that S of U equals X, some X in Rn, and S of V equal to Y. But then what that mean if I apply T on both sides? So this is saying T of S of U is equal to T of X. But on the left side, we know that T of S of U will give me U. So this gives me that U is equal to T of X. And in the same way, on the this side, we apply T. So T of S of V is equal to T of Y. So we get V on this side, and so V is equal to T of Y. So now, for the first one, S of U plus V, I can write it as, because U is T of X and V is T of Y. So S of U plus V will be equal to S of T of X plus T of Y which is equal to S of T of X plus Y. And why is that? Because T is linear, okay? Because T is linear. So which will be equal to, now it becomes S of T of X plus Y. I'm rewriting that. So which means now this is going to give me X is equal to X plus Y according to equation 1. So by 1. But what is X? X is S of U and Y is S of V. Hence we have proved the first condition. The second condition, so we start with S of R of U. So we know that U can be written as T of X. So this is because T is linear, so this will be the same as T of Rx. Because again T is linear, that is the reason we can do that. And now this will be equal to S of, I don't need to rewrite it, it's going to give me basically just Rx, which is equal to then R of times S of U. So we are done with the proof. Hence S is linear. Okay, now we will go to section 2.8.